Hi everybody, my name is Vuong. In today's video, I will talk about our paper, Coupling LSTM Neural Networks and State Space Model through Analytical Tractable Inference. State space models have been well studied in the literature. They have been applied intensively in the field of control and time series. Neural networks have been used with remarkable success in many fields, and there are hybrid models that try to couple these two methods in order to take advantage of these two methods. However, this is not a straightforward task because the nature of the two methods are very different. On the one hand, state space models are probabilistic methods. They use Bayesian inference in order to learn the hidden state, and with linear state space model, we can perform analytical Bayesian inference. On the other hand, neural networks are normally deterministic models, and even with Bayesian neural networks, they use gradient descent and backpropagation in order to learn the neural network's parameters. In our case, we want to develop an integrated method that couples state space model and LSTM probabilistically using only analytical Bayesian inference, and we will do that using the TAGI method. Before going to that method, let's go through the motivating examples. In this time series, it has a linear trends and the seasonality. And without doing any data pre-processing in order to remove the trend, the neural networks give a pretty poor prediction, as you can see in the black line here. And we don't want to do data pre-processing in order to remove the trend. We want to analyze the data as it is. So the idea is to use state space model to model the linear baseline patterns, and that leaves the LSTM to model only the recurrent patterns. And with more complex time series like this case, we still want to use state space model to capture the complex baseline patterns and the LSTM to model only the recurrent patterns. Now, let's make a quick recap of the tractable approximate Gaussian inference or TAGI method. In these figures, I have a feed-forward neural networks where X is the input layer, A are the activation units, and Z are the hidden state, where A are the transformations of the Z, and A and Z are overlaid on top of each other. Then I have Z output, which are the output of the neural networks, and Y are the observations, and theta are the parameters of the neural network, which include the weight W and the bias B. Now, let's see how we compute the hidden state Z here. The hidden state Z here is a sum of the product terms between the weight W and the activation unit A. And in TAGI, the weights W and A are modeled as Gaussian random variable with the mean mu and the standard deviation sigma. So now we are dealing with operations on Gaussian random variables. However, the first challenge is that the product terms between the two Gaussian random variables here, W and A, doesn't result in a Gaussian distribution, so that this operation do not result in a Gaussian distribution, and we lose the tractability here. And the method proposed to use Gaussian multiplicative approximation or GMA equations in order to approximate the product term between two Gaussian random variables by another Gaussian distribution with the mean mu and standard deviation sigma, where when the mean and the standard deviation can be obtained using analytical formulations, so that this operation now can be approximated by a Gaussian distribution, and we can keep the tractability of the method here. The second challenge is how to obtain the activation unit A from the hidden unit Z, where A are the nonlinear transformations of Z. And again, the PDF of A is not a Gaussian distribution, and the method proposed to use first order Taylor series expansion in order to approximate that sigma function by a linearized activation function, and with that we can approximate the PDF of A by a Gaussian distribution. And the mean and the standard deviation we can obtain using analytical formulations. And on top of that, the TAGI method can perform analytical inference in order to learn the parameters theta, which are the weight W and the bias B here, by using analytical formulations without relying on backpropagations. The TAGI method has been applied to feed-forward neural networks, convolutional neural networks, and how about the LSTM architectures? It turns out that with any new architectures, we need to develop mathematical formulations for that new architecture in order to apply the TAGI method. In today's video, I will show you how I apply the TAGI method to the long short-term LSTM neural networks architectures. On the left side, I have an LSTM cells. On the right side, I have the LSTM equations, where the first four equations are to estimate LSTM gates, namely the forget, input, output, and candidate gates. And the last two equations are to calculate the cell and the hidden states. Here, everything is there's nothing new. This is textbook materials. But in the TAGI framework, we consider all the quantity in the neural networks as Gaussian random variable. So from lowercase here become uppercase to represent Gaussian random variables. Now just focus on the four LSTM gates. And in order to estimate these gates, we need the input xt, the hidden state at t-1, and the parameter theta. And now we consider all of them as Gaussian random variables, so that we are dealing with operation on Gaussian random variables. And here we can see that all the operations to calculate these LSTM gates, they only include the product of two Gaussian random variables, the additions, and the nonlinear activation functions. And for all of these, we already have the solution in the original TAGI paper, that is using the GMA equations in order to approximate the product of two Gaussian random variables, and use first order Taylor series expansions in order to linearize the nonlinear activation function. And for that, we can model the four LSTM gates by four Gaussian distributions, where the mean and the variances we can obtain using analytical formulations. And in addition, we make an assumption that we consider all the LSTM gates are independent. We make that assumption because when we calculate the cell state and the hidden state, they will involve the cross covariance between the LSTM gates, so that this independent assumption allows us to reduce significantly the computation for the cell state and the hidden state, so that the operations only include the product of two Gaussian random variables and the activation function. And for that, we already have the solutions. Then, for all the quantity in the LSTM, we can model them at Gaussian random variable, and we can obtain their mean and the variances using analytical formulations. Now let's talk about the inference, where we want to update the LSTM parameter theta of the four LSTM gates here. Normally we can follow a sequential inference procedures, where we start from the hidden state of the LSTM edge here. We follow the red arrows here step by step in order to estimate the posterior for the forget gates, for the input gate, and for all other LSTM gates. And from these posteriors for LSTM gates, we can update the parameter theta of the LSTM. However, the problem with this procedure is that it is computationally demanding, because we only want to update the parameter theta, and we are not really interested in calculating the posterior for all the LSTM gates here. So that we are not going to use these sequential procedures. Instead, we propose to use a bypassing procedures where from the hidden state H of the LSTM, we will follow the red arrow here to directly update the parameter theta of the LSTM and bypassing the calculations of the posterior for all the LSTM gates. And for that, we can use the RTS smoothing equation, which require to calculate the cross covariance between the parameter theta and the hidden state H. And for that cross covariance, I already provide detailed calculations in the paper. So far, I have talked about all the calculation inside the LSTM cells here. Now, let's take a look at the overall architectures in general. So, in the forward part, it goes from the input to the output directions. And the goal of the forward part is to calculate the priors for all the quantity in the neural networks. Then, when the observation Y become available, we can use the backwards path to go in the reverse direction from the output to the input layer by layer in order to estimate the posterior for all the hidden states and the parameters of each layers. And the forward path and the backward path happens at a single time step t here. Now let's unroll the LSTM in time. I have the LSTM at time t equal to 1, LSTM at time equal to t, and then LSTM at time equal to capital T. Now we see that there's a connection in time between the LSTM in the sense that the cell state and the hidden state are propagated from one time step to the next one, so that we kind of have a true time connection in LSTM, and we can take advantage of these true time connections in order to perform smoothing in LSTM by following these red arrows here in order to estimate the smoothed estimate for the cell state, the hidden state, and all the quantity in the LSTM, similar to what we have done in state space model using command smoother. And in our method, there's no limitation to stack n LSTM layers together in order to create a deep neural networks. We verify the performance of our method using time series benchmark. In this case, we use electricity dataset and the traffic dataset. We compare the performance of our TAGI-LSTM models with deterministic LSTM models and Bayesian variation or LSTM model trained using backpropagation using the same architectures. And the bold font here indicates the best results. And from these results, we see that our models provide on par performance with other LSTM models trained using backpropagations. Now we have verified the performance of the TAGI method. We are ready to couple it with state space model. And let's see the coupling through a simple motivating example. In the observation models, we have the observation y equal to the baseline plus a patterns plus an error term v, where the baseline and the patterns can be seen in these figures. For the baseline hidden state, we're going to use the ZB hidden state to model it, where ZB is modeled using linear state space model, and we can borrow existing component from state space model, for example level, trend, and exponential smoothing components to model ZB. And for Z output, we will use the TAGI-LSTM neural networks to model it. So to sum up, our hybrid models consists of two parts, the state space model part and the LSTM part, where the state space model part is used to model the ZB hidden state, and the LSTM model is used to model the Z output hidden states. And both of these hidden states are contributes to the observation Y. Now let's take a look at the transition models. For the state space model part, we have the same transition model as in state space model, ZB at time t equal to A times ZB at time t minus 1 plus WT, where A is the transition matrix, W is the transition errors. And for the LSTM part, the Z output is now an output of the LSTM neural networks, as you can see here, Z output here, where X is the LSTM input, H are the hidden states, C are the LSTM cells, and theta are the parameters. And with these transition models, we can perform the prediction step in order to estimate the prior for the baseline hidden state. We can estimate the prior for the Z output hidden state. Then we can estimate the joint PDF between these two hidden states. And the missing here is the cross covariance between this baseline and the Z output hidden state. And we know that we cannot compute exactly this cross covariance. So at the beginning, we try to approximate this cross covariance, and then we use MC samplings in order to verify our approximation. And then we realize that cross covariance is very small, so that their values can be negligible. And considering that cross covariance or not considering that cross covariance leads to almost identical results. And in this method, we realize on a simplified assumption that we consider zero covariance between these two hidden sets. And from that joint PDF, we can perform the update step in order to obtain the posterior for the baseline hidden state and the Z output hidden states, as you can see in the side arrow from the observation Y here. When we have the posterior for the Z output hidden state, we can apply the backward pass in TAGI-LSTM in order to go layer by layer and update the hidden state and the parameter theta of the LSTM using analytical formulation without relying on backpropagations. We verify the performance of our method with a data with a linear trend, like in this case. We can make prediction in the test set, as you can see in the blue line here, and we can decompose the data into components. The level hidden state to model the linear trends of the data, and the LSTM to capture the recurrent patterns of the data. And for more complex time series, like in this case, we can use the level hidden state to capture what is the overall linear trends of the data. But that linear trend is not enough. We include the exponential smoothing component in order to model the complex nonlinear baseline pattern of the data, and the LSTM to models only the recurrent pattern. And for the ZE hidden state, it is based on the exponential smoothing from the ETS method, where in the original method, the coefficient alpha is a parameter of the models. In our case, instead we model alpha at a hidden state Z alpha, and the product terms here, we can use GMA equations to approximate it, similar to what we have done in the TAGI-LSTM neural networks. And then we can learn that alpha parameters using a hidden state. And at the end of the day, we have a parameter-free exponential smoothing component to capture the nonlinear trends in time series. We verify the performance of our method using time series benchmark, and we compare with other state-of-the-art method. Our TAGI-LSTM SSM models, it uses a local setup fitting a single model to a single time series. And as we can see, our models provide better performance compared to other local models, in this case ARIMA and ETS methods. We also compare our models with other models using mixed and global setups, deep state, ESNN, deep AR, and N-bits. Global model means fitting only a single model to all time series in the dataset, and mixed setup is kind of mix between the local and the global setups. And our model using the local setup can provide competitive performance with other models using mixed and global setups. So it highlights the data efficiency of our model, that we can use a local setup fitting a single model to a single time series and still achieve competitive performance with state-of-the-art method. We conduct the MCB statistical test using the P90 quantile loss matrix, and this test compute the average ranks of all the methods. And we see and the two dashed line here, they indicates the 95 confidence interval of the best method. And we see that for this three data set, our method provide on competitive performance with other methods. Our method is able to quantify the aleatory uncertainty. So recall the observation models y equal to the baseline plus patterns plus an error terms. And in heteroscedasticity cases, the error terms can be modeled by a Gaussian distribution with zero mean and the standard deviation sigma v, where sigma v changes in time as a function of the input x. And in our method, we can model V using the LSTM neural networks. And then when the observation Y become available, we can update that error terms similar to what we have done with the ZB and the Z output hidden states using only analytical formulations without relying on backpropagations. And for more information about how we quantify that uncertainty, I invite you to take a look at the paper by Descartes in neurocomputing. This is an example of how we can quantify the uncertainties in time series. On the left side, I have a part of the training set in red. And on the right side, I have the prediction in the test set, as you can see in black line here. And the blue bounds here are the total uncertainty, which include the epistemic and the aleatory uncertainty. And you can see that the uncertainty changes over time. And we can separate what is the epistemic uncertainty, as you can see in the small cyan areas here, from the total uncertainty. So in conclusion, we have proposed an analytical tractable Bayesian LSTM or TAGI-LSTM neural networks. We have proposed the probabilistic coupling between TAGI-LSTM and state space model. In our model, we can quantify both epistemic and aleatory uncertainties. And for all of these tasks, we can achieve these tasks using analytical Bayesian inference without relying on backpropagations. And the TAGI-LSTM models is available in the CoolPy Python package. And for more information, I invite you to take a look at the TAGIML.com website. Thank you for your attention.